The UltraScale architecture introduces many innovations over traditional FPGA architectures that increase performance and reduce power consumption. In this video, we will focus on enhancements to the routing, with UltraScale architecture providing a 2 times increase in routing capacity, the logic, where UltraScale incorporates an enhanced configurable logic block for tighter packing of logic elements within a design, and the implementation software to take full advantage of these architectural innovations. These innovations result in an architecture that allows for a highly utilized device while still maintaining performance and keeping runtime low. But first, let's look at what motivated our innovation. Looking at the types of applications that our customers are deploying today, we're seeing a tremendous uptick in bandwidth requirements for networking, video, and wireless communications. As our customers scale up and want to get into more advanced applications, we need to provide additional features and capabilities in our solutions to enable them to realize these higher throughput systems. All the types of applications that our customers are demanding are really driving a trend internal to our devices to wider, faster buses. And just to put that into perspective for you, look at the relative data here that is driven at 10G, then 100G, quadrupling as we get to 400G, and then another exponential growth as we go to the terabit systems in terms of bus width. As bus widths grow, the clock period available in which to manipulate this data is decreasing at an exponential rate. So these two forces are really combining to put tremendous stress and strain on the core fabric architecture of our silicon devices here as we move into these next generation nodes. And we need to design a silicon architecture that's going to meet those needs. As we move into the future, the challenges are getting more difficult to solve. We're seeing routing delay beginning to dominate the overall delay within the device itself. Clock skew becoming a larger issue as we get into smaller timing budgets and larger devices. And finally, we also need to be able to optimize the packing within our devices as they continue to grow in density. All of these challenges really require the combination of both software and silicon to address them. And that's what we set out to do. The first part of the solution came when we brought to market at 28 nanometers the Vivado tool suite. That was a very significant contributor to our success at 28 nanometers. It enabled us to break down some of those interconnect bottlenecks in the 28 nanometer timeframe for the types of applications that we were facing there. Here's how. Traditional tools are based on a random initial placement and random moves that can only optimize for one global variable, typically timing. But the other related variables, such as localized congestion and wire length, cannot be taken into account using this approach. With Vivado, we retooled and designed a placer capable of mitigating congestion. Vivado's analytical placer is a mathematical solver to find a solution that optimizes for 3 variables concurrently: timing, congestion, and wire length. Next, it was time to further innovate with our silicon. Here's where the UltraScale architecture comes into play. The UltraScale architecture was designed to serve those future requirements we talked about, providing the types of fabric and DSP performance, I/O and bandwidth required for next generation applications. We took a hard look at why interconnect is so often dominating the total path delay. As density grows in a conventional architecture, the interconnect tracks grow by about order n, but the logic elements grow by order n squared. So a significant gap develops between the amount of logic elements available versus the number of available interconnect tracks. In UltraScale, we're closing the gap by adding more direct routes to the interconnect structure and by leveraging the analytical co-optimization of Vivado to identify the most optimal route from point A to point B. Next, let's talk about what we call ASIC-like clocking. As we scale up to support more demanding, higher bandwidth applications, we need a robust clocking infrastructure that scales with device density. Past architectures were typically built on a central clock spine that would fan out to drive any of the logic within the device. The further the logic was from the spine, the more the clock skew became a challenge. UltraScale's clocking infrastructure is distributed on a per clock region basis. So as we add more clock regions to the device, we get more clock resources. The clocking infrastructure scales with device density. This allows us to center the clock network about the user's logic rather than it being fixed to the center of the die. We can now deploy clocking resources only where they're needed, centered about the user's design, better able to optimize SKU across the customer's design. Lastly, we've tackled the logic infrastructure itself, making it more flexible to enable more efficient logic packing. Tighter packing brings about shorter net delays and less wire switching, that in turn enables higher overall utilization, higher performance, and lower power consumption. To put the architecture and tools to the test, we downloaded a low-complexity design core from opencores.org. We synthesized its RTL with Vivado and the competitor's tool to verify that both tools produced about the same number of LUTs for the design. Then we stamped the core multiple times into a test design, running through Vivado and the competing implementation tools, targeting a 1.15 million logic cell device, while iteratively adding more stamps to the test design until each tool failed to route. Along the way, we monitored device utilization, actual LUT count, and tool runtime. Here's what we found. The competition device fit 265 stamps of the core. The similar-sized UltraScale device fit 285 stamps, holding 8% more than the competitor's device, even though both are about the same size. Now look at the actual LUT utilization. The Xilinx device was able to use nearly all the LUTs in the device. The competing device failed to route after just 60% of the LUTs were utilized. Now, let's take a look at routability and runtime. We measured routability and runtime over a broader set of designs. You can see that over the sampling of designs, with varying complexity and size, Vivado was able to route nearly all of the sample sets successfully. But even across this broader sampling of designs, like we saw previously, the competing architecture struggles to successfully route designs above 60% LUT utilization. And even on designs of moderate size and complexity, the software runtime increases dramatically as the software struggles to use the architectural resources. So, what does this all mean to you? Simple. With the UltraScale architecture and Vivado tools, you will be able to use more of the device resources you pay for and fit more design into the same size device. You'll see better area and power efficiency with no wasted LUTs. And your development schedule will benefit from shorter tool runtime, giving you faster design iterations. Go ahead and run the benchmark design yourself and compare the results using the two tools. You can obtain the design we used, as well as all the tool scripts and reports from your Xilinx FAE. Thanks so much for watching.